Now that you have seen some examples of nonlinear estimation problems and the associated observation equations, in this video we will introduce the principle of nonlinear least squares estimation. So the question is how to estimate the unknown parameters x if the model is nonlinear. The system of observation equations will now look like this if we have m observations. You can see that each observable is a function of the n×1 parameter vector x. The principle of nonlinear estimation will first be introduced for the most simple situations, where we have only one observation, which is a nonlinear function of one unknown parameter x. Hence, y is observed and x is unknown, and a is the nonlinear function. This is an inverse problem, and if function a is not invertible, it cannot be directly solved. The trick we will apply here is to approximate a with a linear function, assuming that this is a good approximation in the neighborhood of x. Let's see how that works. First, we will make an initial guess of x, and here our guess is called x0. This guess, x0, can be inserted in the function a, since this is the so-called forward model. In this way, we obtain the function value at x0. It is at this point that we approximate the function a by a linear function as follows. We take the derivative of function a to find the gradient at x0. And this is the slope of the tangent line at x0, the blue line shown here. So the idea is that the tangent line is an approximation of function a. Remember that the observation we had was given by y. Let's briefly look at the tangent line only. By definition, the gradient is equal to delta y over delta x, as visualized here. The equation is as shown in the top left of the. In the figure you can see that delta y is equal to y minus a at x0. And this is the difference of the two function values we have. If we use this result in the top equation, we get this result. We now have that delta y is a linear function of delta x. So we can easily calculate delta x. And what does that give us finally? Well, it's a new approximation for x called x1. It's equal to our initial guess x0 plus delta x. And this x1 could be our estimate of x. Here you see the result with the actual function a shown as well. Note that this approximation with a linear function is in fact the so-called first-order Taylor series approximation. If you're interested, a short note on Taylor's theorem is included in the reading materials. Now, having the estimate for x, we may ask ourselves though, how good is this estimate? What we can do is to solve the forward model again to get the function value y1 at x1. We can then see how y1 deviates from the observed y. And what we could do now is to repeat the whole procedure, but now with x1 as our new guess. Again, we approximate function a by a linear function, in this case the tangent line, at x1. This will then give us x2, which is indeed much closer to the true x. And this process can be continued. Hence, the procedure is as follows. We start with our initial guess x0. Based on the linear approximation, we find delta x1, which provide us with a new approximation of our unknown parameter. The new x1 is then used to get a better approximation, x2, and again the same equations, but now x0 is replaced by x1, and from that we get x2. And we continue and continue. It is thus an iterative procedure. But after how many iterations do we stop? We will do that once the delta x becomes very small. And our final estimate of the unknown x in this case will thus be equal to xi. Note that in this procedure it is straightforward to calculate the delta x in each step, since we are only dealing with a function of one variable. Delta x at step I can thus be calculated with this equation, in which we will denote the numerator with delta y, and let x now be a vector with n parameters. The first order linear approximation is then given by this equation. Note that here delta x is an n by 1 vector. The vector highlighted here is the so-called gradient vector, with partial derivatives to the individual elements of vector x. This gradient vector is also referred to as the Jacobian. In this way, again, we express delta y as a linear function of delta x. We call this the linearized observation equation. This means that we can now apply linear least squares estimation to estimate delta x from the observed delta y. The only problem in this case is that we have one observable and n unknowns. Therefore, it is time to get back to our original problem, where we have m functions in n unknown parameters. Similarly as on the previous slide, you can set up the linearized observation equations for each observable. And this gives you then, again, a linear system of m observation equations in n unknowns, which can be solved with linear least squares estimation. The iterative procedure as we presented for the scalar case is still applicable and will be presented in the next video, where we will also look at some properties of nonlinear least squares estimation. But let's first work on some examples in the exercises.